In this next section, we're going to consider an interesting phenomenon. And that is, we studied before that water is perhaps the most common amphoteric substance. In other words, it can behave in reactions as the acid or as the base. In other words, as the proton donor or the proton acceptor. But it's interesting to study the properties of water, the quote-unquote acid-base properties in water. It turns out that even in pure water, you're going to have this equilibrium present. Notice how the water molecule dissociates into hydrogen and hydroxide ions. We call this the autoionization of water. Now, the expression that I show here is abbreviated. This is really what is happening. Consider two molecules of water interacting with each other, with essentially the one on the left taking over that proton from the one on the right, and the one on the right keeping the electrons. So what you have as a result is, as you see on the right, a hydronium and a hydroxide ion. If we were to look at it with these models here, we can see that in this equation, there's actually two molecules of water participating, right? And we would say that one of them is going to be acting as the acid or the proton donor, and the other one is going to be acting as the base. Now, the proton donor one produces hydroxide ion, which would then be the conjugate base. The other molecule of water would act as the base. It receives a proton from the second water molecule and produces hydronium ions, which would then be the conjugate acid. So we can treat the autoionization of water the same as we would with any other weak acid. Now, let's talk about the equilibrium that we just illustrated here, the ion product of water. So we have this equilibrium. Again, I'm going to use the abbreviated form as if the water molecule were just splitting as opposed to two water molecules reacting. The Kc of this, because the water concentration itself is constant, the Kc of this is going to be actually the product of the hydrogen ion times the hydroxide ion concentrations. Because this is a very special case, we're going to call it Kw, and it's going to be named the ion product constant of water. It's the product of the molar concentrations of hydrogen and hydroxide ions at a particular temperature. Remember, we discussed in the unit of equilibrium that the equilibrium constant is sensitive to temperature. So what we know is that at 25 degrees, this ion product constant Kw is 1.0 times 10 to the negative 14. Now remember, we dissolve many things in water. So let's say we dissolve a substance in water that has no impact on the level of hydrogen ions or hydroxide ions, which, as we said before, as we showed in our demonstrations, we can detect the presence of either one of these ions by using, litmus paper or an indicator. So in most situations, the hydrogen ion and the hydroxide ion concentrations are the same. We're going to say that this solution, for example, when you dissolve sodium chloride in water, there's no impact on these ions. We would say that this solution is neutral. Now remember, when we added hydrochloric acid to water, we produced extra hydrogen ions. So in that situation, the hydrogen ion concentration is larger than the hydroxide ion concentration. And we would say that solution is acidic. Now, when we added sodium hydroxide to water, we had extra hydroxide ions. So in that case, the hydroxide ion concentration was larger, and we say that solution is basic. Another word is also alkaline. Now remember, at 25 degrees, the ion product has to be a constant. So that means that if I increase the concentration of one of those ions, either the hydrogen or the hydroxide ion, that means that the others the other item's concentration has to decrease in order to maintain this product as a constant. So what would be the concentration of hydroxide ions in an acidic solution whose hydrogen ion concentration is 1.3 molar? All right, let's see what that is. Remember, Kw, the ion product constant, is 1.0 times 10 to the negative 14. If the question did not specify, assume that we're talking about room temperature or 25 degrees Celsius. We're being told that the hydrogen ion concentration is 1.3 molar. So I want to find out what is the hydroxide ion concentration. So this is just basic algebra. We're going to rearrange our equation there so that the concentration of hydroxide is given by Kw divided by the concentration of hydrogen ions. So Kw is 1 times 10 to the minus 14. Hydrogen ion concentration is 1.3. Remember, at this point, we don't really care. We're not going to be concerned with molarities or units or anything like that. So math gives us 7.7 times 10 to the negative 15 molar. So notice that this solution obviously would be acidic because the concentration of hydrogen ions is higher than the concentration of hydroxide ions. But the important thing is that if you change one of them, the other one has to change also. And by the way, we'll talk about significant figures a little bit later in this lecture. Now, as you can see, measuring ranges of concentrations that go from, the 1 and 2 molar to the 10 to the negative 14, 10 to the negative 15 molar, it'd be kind of very difficult. And so because of that, we've created a scale to measure the acidity of solutions. It's called the pH scale. This is our measure of acidity. Now, for our purposes, we're going to define pH as the negative of the logarithm base 10 of the hydrogen ion concentration. Couple of things. Number one, the actual definition of pH has to do not with the molarity of the hydrogen ion, but the activity, the chemical activity. If you take an analytical chemistry course later on in your life, you'll understand that a little better. Secondly, notice that this is the logarithm base 10. This is not the natural logarithms that we were using in kinetics and in radioisotope analysis before. So, if the solution is neutral, that means that the hydrogen ion concentration and the concentration of hydroxide is the same. Since the product of those at 25 degrees has to be 10 to the negative 14, in order for them to be the same, that means that the hydrogen ion concentration has to be 10 to the negative 7 molar. So if you take minus the base 10 logarithm of that number, you reach a pH equals 7. So a neutral solution has a pH of 7. Let's look at an acidic solution. In this case, the concentration of hydrogen ions is greater than the concentration of hydroxide ions. So that means that the hydrogen ion concentration has to move up above that middle point. So it has to be, therefore, greater than 1 times 10 to the negative 7 molar. So if we take minus the log of that, remember, the logarithm of 10 to the negative 7 would be negative 7. But because we're taking the negative of that, it becomes 7, but you also have to invert or flip the greater than sign into a lesser than. In other words, the pH is going to be less than 7. So an acidic pH is a pH that is less than 7. If the solution is basic, then the concentration of hydrogen ions is lower than the concentration of hydroxide ions. Mathematically, that means that the concentration of hydrogen ions has to be less than 10 to the negative 7. And applying our analysis of pH, that means the pH has to be greater than 7. So it's a little bit of a strange scale because in this scale, the more acidic a solution is, the lower its pH. In other words, as you increase the pH of the solution, that means that the concentration of hydrogen ions or the acidity of that solution is going to be lower. Okay, so here is a chart that shows the pH of some common substances, and many of them you can imagine they pretty make sense. You know, limes, lemons, many fruits have acidic pHs. What would come perhaps as a surprise is that rainwater, in other words, water that we get from natural sources, actually has a bit of an acidic pH. We'll probably discuss that later, but in case I forget, just realize that the carbon dioxide in the air has a limited range of solubility in water, and when it dissolves in water, it becomes carbonic acid, which is an acidic substance. You'll notice that human blood is actually slightly basic or alkaline, and that pH range of 7.3 to 7.4 is sometimes called the physiological pH. This is the pH that the body maintains for human blood, so everything works well. Okay, this is an old school pH meter. We do have some more advanced models nowadays, but essentially this is an electronic probe that when you submerge it in the solution, it generates a small circuit that the machine detects and converts into pH units. In the lab, we have some more sophisticated versions of this. They actually look like pens, and so if you do these experiments in the lab, you will get to use that equipment. Another important relationship is we could actually have built the scale not on acidity, but on how basic solutions are, and we could have defined the pOH as minus the base 10 logarithm of the concentration of hydroxide ions, right? So we could have chosen that. I think that because the majority of substances we work with are more in the acidic range, acid was used. It's also probably easier to build a probe for acidity than for how basic something is. So we know that the ion constant product is hydrogen ions times hydroxide, and it is 1.0 times 10 to the negative 14. By the way, that 1.0, just count it as an exact amount. Put as many zeros as you want after that if you want. So let's say I take the minus the logarithm on each side of that equation. Of course, on the right side, minus the log of 10 to the negative 14 is 14. But on the left, we would have minus the log of a product, which means that we're going to add the logs of each one. And because we flip with the negative, we end up with this expression here. But notice that minus the log of hydrogen ions is the pH, and minus the log of OH minus is the pOH. So essentially what we're saying is that the pH plus the pOH equal 14. Interesting, right? So that's a very useful expression. We are typically going to work with pH only. We're not going to be calculating pOHs most of the time. We'll do a few practice exercises, but the important thing here is that this expression is going to allow us to solve some interesting problems. Okay, practice time. The pH of rainwater collected in a certain region of the northeastern United States on a particular day was 4.82. What is the hydrogen ion concentration of the rainwater? Okay, give you a moment to pause. Here is the formula for pH. If you want to pause the video and do the calculation, and we'll come back. Okay, notice that in this case they gave us pH, and that's minus the log of the hydrogen ion concentration. So in order to find the hydrogen ion concentration, we had to take 10 to the negative of the pH. Again, if you forgot how to do this in your algebra or advanced math, please go back and review it. So 10 to the negative 4.82, and our calculator will have a number. We're going to round it to 1.5 times 10 to the negative 5. I know. You're going to say, Dr. Dia, wait a minute. 4.82 has 3 sig figs. How come in this case, for this guy, we just did 2 sig figs? Don't worry, I will explain it in a moment, okay? Don't panic. There is an explanation. Let's try this one here. The hydroxide ion concentration of a blood sample is 2.5 times 10 to the negative 7 molar. What is the pH of the blood? Okay, there are a couple of ways that you can do this. Let me show you one of them. Of course, one of them is simply plug this number into the Kw expression and then solve for the concentration of hydrogen ions and then calculate the pH. But I'm going to use this expression we just derived. pH plus POH equals 14.00. Okay, I'm putting as many sig figs as I need in there. So what is the POH? Well, it's minus the log of the hydroxide ion concentration, which is minus the log of 2.5 times 10 to the negative 7, which is 6.60. Yes, I know. Here you go again. Wait a minute. This number here has 2 sig figs. How come you're putting 3 in this guy here? Don't worry. All will be explained. Wait for it. Be patient, my young Padawans. All right, here we go. So pH, based on this expression we have up here, right? So pH would be 14 minus the POH. In other words, 14 minus 6.60, which is 7.40. Well, that one you can explain because since you had 2 decimals on each one, you had 2 decimals on the product. But how did you get the POH to have 3 sig figs? Well, the answer is it doesn't. It only has 2. Ah, okay. Hold on. Here we go. Take a moment to read through this. I'll read it along, but just want you to try it out. When you take the logarithm of a number written in scientific notation, the digits before the decimal point come from the exponent on the 10, and the digits after the decimal point come from the coefficient. So let's look at this expression. I want to take the logarithm base 10 of 2.0 times 10 to the 6. According to the rules, what I would have to do is take the log of 2 and add the log of 10 to the 6. Well, the log of 10 to the 6 is 6, right? The log of, something to the, 10 to the n is n. And the log of 2.0, we look it up, and it's 0.303030. It's a repetitive number there. So when I add these, I have 6.30303, etc. Notice that that 6 that's before the decimal point, it came from the 10 to the 6th power. Remember, the part of the scientific notation number that determines the significant figures is the coefficient, not the 10 to the whatever. The sig figs are the digits after the decimal point in the log result. In other words, when we do this operation and we get 6.303030, etc., notice that that 6 came from the exponent of 10. In other words, this 6 here is not significant. The significant figures are the digits after the decimal point. And since our number had 2 significant figures, that means that we're going to keep 2 decimals in there. All right? That's why in the previous example, when we had 4.82, we said that essentially only the 0.82 are significant, and therefore our result has 2 sig figs. That's why when we took the log of 2.5 times 10 to the minus 7, the 6 that comes out there comes from the exponent of 10, and therefore we just consider the 2 sig figs and 2.5 in here. And we have 2 decimals in this expression. All right? So maybe you need to take a little pause here and go back through that and analyze and make sure that it makes sense to you. Okay, strong electrolytes are substances that dissociate to 100%. In other words, every single item that goes into solution dissociates. So strong acids are strong electrolytes because, like HCl, they have a complete conversion into ions. You can see that because we write it with a single forward arrow. In the same way, strong bases are strong electrolytes. In the case of NaOH, when you dissolve it in water, it completely dissociates into sodium and hydroxide ions. We write a single forward arrow. Now, water has its autoionization, but remember, we're talking about something on the order of 10 to the negative 0.7 contribution to the hydrogen and hydroxide ions in the solution. So for a strong acid or base, the contribution of water to the total amount of hydrogen and hydroxide ions is negligible. So for a monoprotic acid that is strong, essentially the concentration of hydrogen ions in solution is going to be the concentration of the acid itself. Similarly, for a strong ionic base, excuse me, the hydroxide ion concentration is going to depend on the number of hydroxide ions produced per formula unit of the base. In other words, the pH of the solution of a strong acid or a strong base is going to be derived exclusively from the concentration of the acid or base. The contribution of water autoionization is going to be negligible. So let's say I have a solution that is 2 times 10 to the minus 3 molar, excuse me, in HNO3, which by the time you memorize all this, you will know it's nitric acid. Well, nitric acid is a strong acid. It dissociates to 100%. So when you write the equation for its dissociation or ionization, it's a single forward arrow. So we're going to start at 2 times 10 to the negative 3. And at the end of this, basically, at the start of this, you have no dissociated ions the instant the substance dissolves in water. Excuse me. At the end, there is no acid left. It's all ionized. And so the original concentration of the acid, if we had done this in the style of an ICE table, except that we don't because this is not an equilibrium situation, all of the acid got converted into ions, which means that the concentration of each ion equals the initial concentration of the acid. So the pH will be minus the log of the concentration of hydrogen or hydronium ions, which is 0.002. Again, we go back to our discussion. This number has only one significant figure. That means that our pH only has 1 decimal in its value, and the value is 2.7. Let's consider a base now. 1.8 times 10 to the negative 2 molar in barium hydroxide. Okay, be careful with this one because barium hydroxide has 2 hydroxide units per formula of the compound. It is a strong base. It'll dissociate to 100%. So we have in the balanced equation, notice that we have 2 hydroxides. So we're going to start with 0.018 molar. And of course, initially, there's no extra ions in there. At the end of the process, all of the barium hydroxide has dissociated. There's none left. So we would have 0.018 molar of barium ions. But be careful, we get 2 hydroxide units per formula unit. So the concentration of hydroxide ions would be 0.036. In other words, 2 times 0.018. We can do this, for example, we can say, well, the pH would be 14 minus the pOH. We can use that formula. So 14 minus the negative of the log of 0.036, in other words, plus the log of 0.036, and that comes up to 1260. Again, we had 2 significant figures in this value here, right? So we are going to have 2 here. Actually, this one's different. We're going to use the different rule, right? This is 3 decimal places. This is 2. However, that 14.00, I just wrote it that way, right? I know that my pOH or pH have to have 2 decimals in it. So the 14, I just chose 14.00, but I could have put extra zeros in there if I wanted to. I want to keep things based on my items of interest, in this case, the barium hydroxide. Okay, time to start winding down. What about weak acids? Well, Weak acids and weak bases are weak electrolytes. In other words, substances that undergo less than 100% dissociation. Just a fraction of the molecules will actually ionize in water. So for example, HF, hydrofluoric acid, as you can see, we express its ionization in water with a double arrow. And we do the same thing for, let's say, the nitrite ion, which is the conjugate base of nitrous acid. When it ionizes in water, it gives us hydroxide ions, and we get the conjugate acid back. But notice that this is a reversible process. In other words, we have a very weak electrolyte. We can show this with a chart here. Let's look at a strong acid, and let's say we're going to represent these species here. You can see the little legend on the bottom there. On the left side, you can see the ionization of a strong acid. So at the moment that you start, you have all HCl, and at equilibrium, you have equal concentrations of hydrogen and chloride ions. Notice in the picture, you have water molecules, right there. You can see the pictures down here. This is water. So for example, these are water molecules. Notice that everything is either hydronium ions and chloride ions or water molecules. There are no unionized HCl molecules anymore. Now let's do this with a weak acid. Let's take hydrofluoric acid. And you can see here that before ionization, of course, you have the molecules of HF. And at equilibrium, what you find is that you look at the picture here, you have a few, fluoride ions. I see one here. And then you have a few hydronium ions. You see one in here. Actually, I think in this picture, that's all you see. That one and that one there. And everything else, it's either water or the unionized molecules of HF. So at equilibrium, you have a mixture of these. You have a few ions, but most of the acid remains unionized. All right. So this is our conclusion for this section. I think now that we understand the autoionization of water and the use of pH to measure the differences between strong and weak acids, between acids and bases, I think we are ready to do some equilibrium state mathematics, and that'll be our next section.